Okay, so let's make a new script, or actually make a new function. That's what we'll do. This is going to be our Fermi function. So we'll call it Fermi. And the inputs to this, well, we're going to take an energy vector. We're going to give it a Fermi energy. And then we don't care so much about t as we care about kt, right? So we're going to give this a single output, and it's going to be f. So I'm going to put copy here in the help. It's going to be f equals Fermi that we'll say this calculates the Fermi function for energy vector E with Fermi energy EF and temperature or smoothness parameter KT. So the way we calculate this is F equals, we'll take something and we're going to invert it. And that something that we invert is the exponential of something divided by KT. That something divided by KT is E minus EF oh, and then we have to add 1 to it. And that, remember that plus 1 is in the denominator. So once again, it's the exponential of EF, or E minus EF divided by KT. You add 1 to that, and then you invert it. So that's why I have this there. We can save that. Save it wherever you like. I need to change to the appropriate folder. I'm going to save it. Now it's going to save there, and I'm going to save it as, well, it already picked the name. I picked the name because I called it Fermi. So I don't know if you've written MATLAB functions before, but one nice thing is you can type help and then the name of your function, and then it gives you this help text that we typed in at the beginning. It's kind of fun how it stresses the function name. It bold faces it. Anyway, right, so there's that. Let's now make a test function. So we'll call up a new script that tests this, just to make sure it's right. And so we'll call it, I'm going to put up here test fermi.m. I'm going to hit Control S for save. We're going to call it test fermi.m because I was practicing this. I already have a test fermi.m. But anyway, we're going to say x is going to be our energy. It's going to go from, let's go lin space from 0 to 5, and let's say nx, and nx should be, let's make it, I don't know, 301. And we'll have some Fermi level, so xf, let's make that 2 for now, and then the smoothness, kt, we'll call that let's call it 0.001 for now. So like, I guess that's 1/10,000th. So this is the smoothness. This is the Fermi value. So let's just calculate it. F equals Fermi. And then, oh, isn't that nice how, see, MATLAB, it reads my function, it tells me what I need to give it. So X is our E, and then now it's highlighted, okay, I need to give it EF, so that's, in our case, it's XF, and then KT, okay, and let's plot X as a function, F as a function of X. We're going to give it line width 2. We're going to turn the grid on, and we're going to set the current axes font name to be times, and we're going to enlarge the font. So font size 18. And let's just see what that looks like. Run it. Here is my plot. And we'll just play with some of the parameters. Let's turn up KT, so our smoothness, right? So let's make it 1/100th and see what happens. Well, it's hard to see that, but maybe you can see it. Let's make it 1/10th, and you see, okay, yeah, now it's starting to become smooth. And as we said before, the Fermi level, so XF is 2, and you can see right at 2, the value of our Fermi function is 1/2. Okay, so that's our Fermi function seems to work. And we'll just put here labels, so X label, $X, interpreter, did I spell that right? Interpreter, tech. Let's see if that runs. Yeah, that runs. And then Y label, we'll call that F. Right, and so you can play with that. Oh, let's also, I forgot, let's move the Fermi position around just so you can see that. Let's change the Fermi position to 3, and you'll see that it slides over. So we can use this to make smooth things. Great, so we've tested our Fermi function. Let's now start a new function, and we'll make, or sorry, new script, and let's call this. We'll call it E for exercise. Yeah, something like that. Exercise, and today's date is 2017-03-14. It's Pi Day. I spelled it wrong. Exercise, like that. I'm going to copy this. I'm going to hit save, paste it, .m. Okay, so we're going to make a problem, but the very first thing I'm going to do for this problem is let's set a frequency scale, frequency scale for the problem. So we're going to say F1 is, I don't know, let's use something like 5 kilohertz. So 5e to the 3. So this is hertz, and this is the frequency scale for our problem. So the frequency scale comes with a time scale, 1 over F1, seconds, time scale for our problem. So let's define now a t-min, and we're going to set that to be -10 times t1, and the t-max to be 10 times t1. And we can define a t to be the lens space from t-min to t-max, and we'll specify nt time points where I need to add a line nt. For now, let's set that to be 301, sort of arbitrarily. Oh, and actually, let's not just make it 301. Let's make it 2 to the, say, 9th, because 2 to the 10th is 1024. That's 2 to the 9 is what, 512. You'll see why I did this later. So it's a power of 2. Turns out we're going to be taking a Fourier transform, and the fast Fourier transform works best when the number of points is a power of 2. That's when it's fastest. So let's make a message. So let's make M. Let's start off by making it Fermi of t, and we're going to put in the transition time. Let's make the transition time negative. Okay, so basically the Fermi time, that is. Let's make it negative 3 times t1. Actually, make it -4 times, or -5 times t1. That works, I guess. And then the smoothness, let's put in t1 over, bless you, t1 over 8 for now. And then let's have a visualization section. So there's a visualization section. There's a let's make a message fig equals figure, and so we'll plot tm line width 2 grid on. You can go back to your test Fermi and get stuff like the set GCA. We're going to get the formatting stuff from before. So the X label here should be T in, for now it's going to be seconds, and then F. Actually, we're going to plot M, and we're not going to specify the units. Should be X label, Y label. See what happens. Let's run this. Here's my figure. Notice the transition time is at -t1, or 3 times t1, I guess. What did I choose? Where's the, oh, -5 times t1. And just to show us, let's see what t1 is. I don't know. Okay, t1 is 0.2 milliseconds. So that's the time scale. And if I don't like to see exponents in the plot, so what I'm going to do instead is instead of plotting t, I'm going to plot t times 1,000, 1e3. That's 1,000, and then we're going to make this time scale to be milliseconds. And here's what my figure looks like now. See, that's a little cleaner. No exponents. All right, so let's change our message a little bit. Let's also add a transition up. So the transition up, like Fermi gives us a transition down, so we'll use a -2 times Fermi, and we'll supply t, but this time the transition time is going to be, let's make it -2 times t1. We'll use the same smoothness, t1 over 8. Let's just see what that looks like. I'm going to run it again and bring back my figure. That's what that looks like now. Let's add a transition down. So I put dot, dot, dot to continue on the next line. And we're going to plus 2 times, we're going to borrow the same Fermi thing here, 2 times that, but we're going to change it. We want the transition to be at positive 2 times T1. And then we're going to take the previous Fermi, the first Fermi, and we're going to subtract it. And we're going to have that happen at 5 times T1. So in the end, I have a signal that looks like this. See how nicely Fermi gave us these smooth transitions. It's centered at 0 in the time domain and also on the y-axis. So there's our message. Let's add a few other parameters. So let's make sure we have. Let's divide this up into sections. So there's a parameters section, and then there's going to be some I don't know, preliminary calculations. Oh. Okay, so let's see. Let's make notes for our Fourier transform. There are some things that we're interested in. For example, there's the T0, the time window, and it's going to be Tmax minus Tmin. Right? So this has units of seconds. This is the time window duration. Of course, that comes with its reciprocal F0. This, if you recall, is the frequency spacing. In the Fourier transform. What else was there? Let's see. There's a sampling period, TS, sampling period, and the way we get that is, well, we take T. It's actually T0 divided by NT minus 1. So this is the sampling period. And that comes with its reciprocal sampling frequency. Okay, so let's take the Fourier transform of M. So we have preliminary calculations, and then I'll have calculations as the next section. So we'll make capital M be FFT, and you might recall that when we do this, you can multiply M by the sampling period, right? You remember when we did that before, that's what we did. And then we're going to make a zero-centric M, so MZC, which is FFT shift of M, capital M that is. And so under the visualization, we have our message fig, and so what I'm going to do is I'm going to insert a subplot I guess, 2, 1, 1, like so. And then let's also copy and paste the subplot command and whatever follows. We'll make it subplot 2, 1, 2, and we're going to plot f and m. We don't have an f vector yet. We didn't define it. Actually, there's probably one existing in memory because we used it in the previous script. But we want it to be meaningful for this problem, so we have to calculate it. So let's see, the f vector, how is that going to work? So let's make it f, not only f, but it's fzc, it's zero-centric. So it's, by default, the Fourier transform returns as many frequency points as there are time points. So we're going to go, it needs to go from negative nt over 2 to nt over 2 minus 1. And we're going to multiply that by f0, or fo, I guess. That's our zero-centric frequency vector. Units are hertz. And so that now then allows us to do our plot, but we have to make sure it's fzc, subplot, right? Subplot 2 and 2, fzc, and we're going to take the abs of m, the zero-centric version, and the x label is going to be frequency in hertz. Y label is going to be absolute value of capital M. So let's see what happens when I run that. So here's my signal, and its Fourier transform. That's not incredibly helpful. Let's multiply the f by 10 to the negative 3, and we'll make it kilohertz. And we're going to zoom in also. Let's zoom into, looks like 20, positive, negative 20 kilohertz. So we'll use the xlim command, and we're going to go negative 20, 20. See how that goes. Here's the signal and its Fourier transform. If I wanted to increase the frequency resolution, what do I need to change in the parameters? That's right. I need to expand the time window, right? Because the time window, t0, right, controls the frequency spacing in the Fourier transform. So let's make it, I don't know, 30, yeah, negative 30, 30, like so. And here's my new plot. You can see that, yeah, it has a higher frequency resolution than the old one, right? And that's cool. Okay, now let's, I'm going to add in here, I'm going to add a close all and a clear all, so we get rid of the previous graphs. And we're going to also add so let's see, we have M, we have the Fourier transform of M. Now let's make a carrier, and let's up top in the parameters, let's say FC, let's set it to be, I don't know, 5 times F1, right? So remember, the message was defined with in terms of F1. So that's sort of like the frequency scale for the message. So we're going to make the carrier be 5 times higher in the frequency domain. See how that works for us. So the carrier, we'll call it VC for the carrier signal. That's going to be, if you like, we can 2 times cosine of 2 times pi. There's our pi for pi day. 2 times pi times FC times t. And then there's going to be a modulated signal, and it's going to be dual sideband suppressed carrier. So we're going to call it VDSB, and all you have to do is take the message, so M, and then you go dot times VC, like that. And then now we can make a new plot, and let's make we'll just copy from here, and we're going to make it not the message figure, but we're going to make it mod sig fig. So it's the modulated signal, and we're going to plot V DSB. So I changed the Y label, so it's V underscore and then DSB dash SC in braces. Let's see what happens when I run this. And we have a fine mess there. We can zoom in, perhaps. Let's see. Use the XLim. And what do we need to do? Let's go from 2 to -2, I guess. So XLim, open close parentheses, brackets, and then -2, 2, run it again. Here's that. One thing you might notice is this signal might actually be undersampled a bit. So I'm going to turn up where NT is. I'm going to turn up, where did NT go? NT, I'm going to go from 2 to the -9s, or sorry, 2 to the 9, and we'll make it 2 to the 11. See how that works. There's a more finely sampled signal. Right, and then we can, let's briefly take the, back to our calculation section. Let's take the Fourier transform of the VDSB. So capital V DSB equals FFT of VDSB times TS, and then VDSB zero-centric version equals FFT shift of VDSB. And then we're going to plot this, and then you'll tell me whether you think it looks like what we expect. So let's take the subplot from the 2, 1, 2 from above, and let's paste it in the for the modulated signal. We're plotting the zero-centric F, and then it needs to be the capital V D, and then if you use tab completion, you can get that. And then this is V underscore DSB dash SC. Let's run this, see what we get. Okay. It's pretty clear to me that I need to expand the limits slightly of our window, so let's make it 50 and 50 kilohertz. So here's what I have. What do you think? Did we get what we expect? Oh yeah, right? Because you see, there's the original message in the frequency domain, and we shifted it left and right to the wherever the carrier frequency is. And next time, I guess we'll start off class next time with MATLAB, and we'll do the demodulation, and we'll need to apply a filter, and you'll see why. Anyway, that's enough for today. Have a great day.